and how you regulate glomerular filtration rate. And then we'll talk about secretion and reabsorption specifically. More specifically, where in the nephron most of the solute and water is secreted and absorbed, and what some key mechanisms are in that system. Okay. I will also say that I posted urinary questions on Canvas. I didn't print them out this time because they're on Canvas. All right, but it's the same type of style, the same critical thinking questions as previously. And again, I would use those as digestive to help you review. And some of the urinary ones are going to be tough because we're not getting the chance to actually practice this in class. And you'll look at what happens if too much hydrogen is secreted or not enough bicarbonate is reabsorbed and how that affects blood pH and all that kind of stuff. So I would suggest that you review them. And if you have questions, then I will not be in tomorrow actually because I have a meeting, but you can email me. And Monday I will be here. You can email me then as well, or you can talk to Elise. I don't have any plans to post answers at this point because I want you to think about it. But I will be available. And if you email me, please write the question you're asking about instead of just on number 3, blah, blah, blah. Because then I have to I can't just do it on my phone. If I have to go to my computer and pull up what the questions are or whatever, it's just easier if you, I'll be faster if you tell me, right? Anyway. So what is glomerular filtration rate?
The amount of flow that passes through the glomerular.
Okay, almost, but not quite. That will get you a wrong answer on the test. That's okay. So Wendy said the amount of flow that passes through the glomerulus. Right? Is that right or wrong and why?
How much is filtered through the glomerulus?
Exactly. So it has to do with the flow that's coming through. That's absolutely right. But it's how much is actually being filtered into the kidney or into the nephron. Okay? So both things are important. If you say just the flow in the glomerulus, thank you, though. Thank you. If you say just the flow in the glomerulus, you're talking about blood flow, essentially. All right? That's just a capillary system. So we're talking about how much filtrate is moving from the glomerulus into the nephron. So how would you calculate glomerular filtration rate? Not even using numbers I've already given you.
Filtration minus reabsorption.
Okay, potentially, or we're just talking about what's moving into the system, so not even what's being reabsorbed or secreted. Glomerular filtration rate is just renal blood flow, right, to that kidney, times the percent of filtrate that's being formed, all right? So if you're looking at 200 mils per minute to one kidney and 16% of that is becoming filtrate, it would be 200 times 0.16, okay? So you should be able to determine kind of what a normal GFR is just by knowing what a normal cardiac output is, what percent of that cardiac output goes to the kidneys, and what a normal percent of filtrate is, okay, from what actually goes to the kidneys. That's what I meant. There are better ways to do that.
Yeah, how would you measure? Is it would dye work?
So you actually can do it with creatinine because 100% is, eliminated. All right, so a normal glomerular filtration rate is about 100 to 125 mils per minute. If glomerular filtration is too high, that means that things will pass too quickly through the nephron, and you may not reabsorb everything that you need to reabsorb. And if it's not reabsorbed, then it ends up in the urine and is excreted. Okay, so that's not good. And if your GFR is too low, that gives too much time for everything to be reabsorbed. And in that case, toxins or byproducts that you really don't need in the bloodstream any longer might also accidentally get reabsorbed. So the body tightly regulates glomerular filtration through 3 mechanisms. One is renal autoregulation, right? And we're going to talk about, you have the same myogenic mechanism. Does anybody remember what the myogenic mechanism is? Right, so that's when pressure goes up. It doesn't dilate, it reflexively constricts, right? So if the afferent arterial, so we're all thinking about the same thing as I'm talking. I'm not drawing this to scale here. I see my efferent's bigger. All right, if the afferent arterial is stretched, basically due to volume, all right, the smooth muscle in the afferent arterial is reflexively going to constrict a little bit. Again, because if there's too much volume, you don't want all of that moving through into the nephron because things will pass through too quickly. So it reflexively constricts to keep flow normal. The same thing if there is too little volume, it will reflexively dilate, and we'll define this in a second. But myogenic is one way, and then another way the kidneys regulate themselves is through something called tubuloglomerular feedback, which will take us back to our juxtaglomerular apparatus and the macula densa. All right, then you also have neural regulation, largely by the sympathetic nervous system, which innervates both the afferent and the efferent arterioles and can result in vasoconstriction. And then you have hormonal regulation by angiotensin II and atrial natriuretic peptide. Okay? So, this is what we're talking about. Again, the afferent and efferent arterial and the glomerulus. And we're going to look at this in terms of a garden hose. All right, so think about it. You have fluid that's moving from fluid that's coming down the afferent arterial, and then it's like you have little holes in the capillaries, and that fluid is able to leave into the capsule. Whatever doesn't leave is going to move into the efferent arterial, right? So if you think about it like a garden hose with holes in it, right? This is the fluid that's spraying out. And if the fluid is not spraying out, it's moving through to the end of the hose, all right? And depending on how big those holes are, or if you step on this hose, what's going to happen to GFR? If you constrict the vessel in front of it, what's going to happen to what's being sprayed out?
It's going to decrease.
It's going to go down, exactly. All right, so I guess I should, let me rephrase this. Here's the faucet. The water's coming in this way, and here's the end of the hose, right? If you step on this end, this is going to go down, right? So if you vasoconstrict the afferent arterial, GFR will go down, right? What if you step on this end? It'll go up, right? So if you constrict the efferent arterial, you can actually increase GFR, okay? Which is a strategy that is sometimes used.
Oh, because it's not going through.
Exactly. It's getting backed up here.
Right.
So yeah, exactly, and it doesn't go through to the end. So sometimes that reference helps people visualize exactly what's happening. So like I said, a normal GFR, everything is the same. If the afferent arterial is constricted, GFR will go down. Okay? If the afferent arterial is dilated, GFR will go up. All right? So again, think about the myogenic mechanism. If you have too much volume, right, afferent arterial will slightly constrict to make sure that GFR stays low, stays where it's supposed to be. Okay? If there's not enough volume, the afferent arterial will dilate to try and allow more fluid to enter the glomerulus, and GFR will go up. Does that make sense? All right, so is everybody on page with the myogenic mechanism? That's a form of renal autoregulation. I'm not going to go over it again. All right, tubuloglomerular feedback is the next form of renal autoregulation. And again, this has to do with crosstalk between the macula densa and the juxtaglomerular cells of the afferent arterial, okay? So in this situation, the macula densa can also detect the rate of flow, by stretch of the tube in the nephron itself or the rate of sodium or other ions passing through the tubule themselves. And if things are passing through at too quickly of a rate, that will trigger the juxtaglomerular cells to respond and alter the size of the afferent arteriole. All right, so what the juxtaglomerular cells do is they release nitric oxide. Nitric oxide, anybody know what action nitric oxide has on vessels? Yeah.
Yeah.
It's a vasodilator.
Dilator.
Yeah, it makes them bigger. So if you have too much sodium flowing through the nephron loop, right, because the macula densa in the loop of Henle, if you have too much sodium flowing past the nephron loop, the macula densa will trigger the juxtaglomerular cells to stop nitric oxide release. All right, they will inhibit nitric oxide release. So now you're releasing less of the vasodilator and the vessel gets smaller. And then less sodium will flow through, which is better for reabsorption. Any questions? And obviously if flow is normal, that signal won't be sent and nitric oxide will continue to be increased and the vessel will stay like this. All right, so this again is altering the size of the afferent arteriole in order to regulate how much is going to be filtered, okay? By the kidneys themselves. No signal from any other system is occurring. You also regulate glomerular filtration by the sympathetic nervous system. And here you see your sympathetic vessels. They actually innervate both the afferent and the efferent arteriole. All right, but what does sympathetic nerve activity do to blood vessels? Always constricts. In the muscles you have, well, it's really metabolite from metabolites, yes. So especially in our visceral system though, it's constriction. All right, so sympathetic nerve activity is going to constrict vessels, all right? So a situation in which you might have high sympathetic nerve activity, you would see constriction of both the afferent and the efferent arteriole, all right? And the idea here is to maintain flow, all right? So you're slowing down what's entering, but you're also slowing down what's leaving, all right? And so that allows flow to be maintained, okay? And this is probably similar to what you would see during exercise, right? So you reduce the flow to your kidneys during exercise, but you're not necessarily, but you're not necessarily going to affect filtration, right? Because you're allowing that fluid to spend more time into the glomerulus to make sure an adequate amount is filtered. Does that make sense? Because you're also putting the brake here, okay? So GFR will stay the same. If you have large changes in sympathetic nerve activity, you will get a much larger constriction of the afferent arteriole, all right? And that will cause GFR to go down. And in this case, your main purpose is to maintain volume, all right? You want to prevent neuron formation in general, okay? So you're going to reduce the amount of all right, hormonal regulation. Angiotensin 2. Angiotensin 2 is a vasoconstrictor. Again, the point here is to increase blood pressure and increase fluid volume. So you want to reduce the amount of fluid that's moving into the nephron and possibly being eliminated as urine. All right, so you will reduce GFR. You'll constrict both the afferent and the efferent arteriole. Okay. Do you have a question?
Oh, no.
Okay. Yes.
On the slide, Laura. the moderate activities, so both of them are being constricted?
Correct.
Okay.
On this one, I mean, both of them are slightly, because you have sympathetic innervation on both vessels, but you have much more on the afferent, so it's much more strongly activated. Yeah. And again, that's like extreme or long-term exercise if you're becoming dehydrated or hemorrhage or very low blood pressure, something like that, where you really lost a lot of volume. All right, and then the last one is atrial natriuretic peptide. You guys remember when atrial natriuretic peptide is secreted? From the heart? From the atria? In what kind of situation? Yes, sir.
Is it when the atrium gets stretched into my blood?
Exactly. When the atria gets stretched because you have a higher than normal plasma volume, right? And the effect is going to be to try and increase urine output, right? So you can reduce plasma volume. So you actually get some relaxation, all right? And that allows GFR, hopefully not to increase too much, but again, you want to increase urine output. So you're going to allow for a slightly higher filtration rate. All right. Any questions on that? Okay, so we're going to move on to reabsorption and secretion. Okay. So, in your nephron, what area is this nephron? Is this part? Proximal convoluted tubule. You have the nephron loop. All right, what is this part? Distal convoluted tubule, collecting duct, and then potentially the papillary duct at the end, okay? All right, so what is reabsorption?
Descending.
Say that again?
Descending.
Say that louder?
Descending loop.
Everywhere. It's actually, yeah, it's everywhere. But what is it specifically?
Water or solids coming back into the blood.
Exactly.
Vasorectal. Vertebral capillary.
All right, so you have, excuse me, filtrate, right? That's entering the glomerulus. All right, so reabsorption is filtered substances that are moving from the nephron into the peritubular capillaries. And these peritubular capillaries are all around the nephron. Okay. So one of the important parts of reabsorption and secretion is what's called the countercurrent mechanism. All right, so filtrate moves in this direction, right? And then it starts moving down the nephron loop. And then it starts moving up the nephron loop. Right? And this is key to establishing a concentration gradient. okay? So you have this nephron embedded in kidney tissue, right, or interstitial fluid is here, and then the capillaries, okay? So whatever is being filtered is first entering this interstitial space before it enters the blood, right? So again, remember, water follows solutes, okay? So if sodium and glucose and chloride are being reabsorbed in the proximal convoluted tubule, what is going to follow them? Water, absolutely. So they're moving into this interstitial fluid. There's a concentration gradient there now, and water is going to move to the area of higher solute, all right? So most water reabsorption is what's called obligatory, all right? And it's through osmosis, and I'll show you that in a second. All right, via osmosis, and it's obligatory. Okay? Now, what is secretion? What is it?
It's from the, like tubules is back into the capillary.
Oh, okay, not quite. No. It's from the paratubular capillaries into the tubule. All right, so secretion is this direction. So this is solutes in plasma, right, that are then moving back into the nephron. Okay? And again, this often happens if anything that did not get filtered got missed. If it's something that's not wanted, there's still opportunities for it to move back into the nephron, okay? All right. So again, the countercurrent flow is essential to establishing the concentration gradient. Any solute that leaves first enters the interstitial space, and that provides a gradient for water to then move through the system. All right. In addition to that, in the loop of Henle, you have changes in permeability. Okay. So the descending loop of Henle is impermeable to solutes, but is permeable to water. Okay. All right, whereas the ascending loop of Henle is permeable to solutes, but impermeable to water. Okay, and it's thicker than the other side is. And this is largely in the juxtamedullary nephrons that it's like this, and they're important in urine concentration as well. Okay, so solute, again, think about it like this. So solute is leaving through the ascending loop of Henle and establishing the concentration gradient for water to leave from the descending side. Does that make sense? So you need the flow that's going upward that way to trigger water reabsorption from the descending loop. Okay?
Would you write the flow of blood on there just so I can see it?
Yes. So blood that's flowing. I guess it depends on where the capillaries are looping around, because they actually loop around kind of like this way, I think. Yeah. All right. So first we're going to talk about what happens in the proximal tubule, and then we will make our way down to the loop of Henle and the distal convoluted tubule. So those things that are reabsorbed are the good things, the things you want, your body wants to keep. Things like glucose, again, 100% of glucose should be reabsorbed, right? Glucose, electrolytes, vitamins, water, amino acids, any small proteins that happen to get into the filtrate will hopefully be reabsorbed as well. Most of your filtrate is reabsorbed. Most of it is reabsorbed before you even get to the lubricant. All right? All of the glucose you reabsorb is done in the proximal convoluted tubule. Okay? All right, so what is secreted? Stuff that you don't want. All right, ammonia, urea, hydrogen ions are secreted, potassium ions are secreted. Any kind of drugs that aren't filtered through the first pass, all right, are also secreted and eliminated in the urine. Okay. Again, since only about 20% is actually filtered, it's nice to have a fail-safe as things come around that they can be secreted into the tubule later after the day. All right, so how do things move through the cells of the nephron? All right, there's two types of methods for reabsorption. One is paracellular, so the solutes can actually move in between small channels through in between the adjacent cells. All right, so that's paracellular reabsorption. Or you have transcellular reabsorption, in which the ion has to actually travel through the lipid bilayer into the cytosol, through the lipid bilayer on the other side, into the interstitial fluid, and then into the capillary. All right. And a lot of these molecules do need some type of active transport or secondary active transport or facilitated diffusion, so they'll move through transcellular reabsorption. Okay, things like glucose specifically. All right, so the other thing you need to remember is some substances move passively, largely small ions or gases are going to move passively through the cells, but most substances are going to require some type of active transport or secondary active transport. In order to power that active transport, you need to have sodium, potassium, ATPases, right? So sodium, potassium pumps generate the sodium concentration gradient needed for other solutes to move inside the cell, right? They usually follow along with sodium's concentration gradient. So the sodium potassium pumps are always on the basolateral membrane, all right? So where is the basolateral membrane? Which side is it on? Is it facing the inside of the nephron, or is it facing the peritubular capillaries? All right, it's facing the peritubular capillaries, okay? All right, so the apical surface is facing the lumen. All right, so this would be your lumen, the inside of the nephron, and the basolateral surface, all right, is facing the peritubular capillaries. So your sodium potassium pumps are always here, all right, which means this is always driving sodium to leave the cell, okay? So sodium is going to be leaving, and potassium is going to be entering the cell. Okay? So again, substances that are usually reabsorbed, sodium. Substances that are often secreted, potassium, all right, is often leaving the blood and going back into the nephron tubule. Okay? And then most of your other substances can follow that gradient. Again, a lot of these transporters have a maximum rate, all right, like we mentioned with glucose. They can take glucose and drop it back off into the capillary system, but they can only move so quickly. So if there's too much glucose being filtered, it's going to end up being eliminated. All right, and that's how you get increased glucose in the urine if you have diabetes. Am I moving too fast? You guys okay? All right. All right, so water reabsorption. Like I mentioned, most water is reabsorbed through osmosis by following the solutes as they're also being reabsorbed. All right, that is obligatory water reabsorption. It occurs largely in the proximal convoluted tubule and the nephron loop. okay? You also have what's called facultative reabsorption. Facultative reabsorption occurs in the collecting ducts, all right? And one of the functions of antidiuretic hormone is to trigger the insertion of a channel that's called the aquaporin channel in the collecting duct, all right? So usually the collecting duct has relatively little permeability to water, okay? But ADH will cause the insertion of these pores, little holes. All right, and that will allow water to leave and enter the capillary system. All right, so when do you secrete ADH? In situations where you need to increase blood volume, right? For some reason you're dehydrated or you're losing blood. And so you can do that at the end of the nephron and directly reabsorb water that way. That is facultative water reabsorption. Okay?
You have to increase blood volume.
Yes, you do that to increase blood volume, exactly. Right, and if you drink plenty of water, if you haven't done anything, ADH is not being secreted, the aquaporins aren't there, and you usually have a larger, more dilute urine output, right?
Are the aquaporins still passive transport though?
Yes, absolutely.
You know about how long this would take to happen?
It's not long, in the matter of hours. Yeah, so not that long.
Opening up points already there, actually putting those transmembrane proteins and actually making them, and then
Yeah, that's a good question. So I know that ADH actually triggers the making of more aquaporins. I don't know exactly. I would imagine some are already there that are being inserted, and it's not a make and insertion process.
that takes
Yeah.
forever.
All right, so let's look a little closer at the proximal convoluted tubule. All right, so what's being filtered or what's being reabsorbed there? Again, most everything is being reabsorbed in the PCT. About 65% of your water and solutes is being reabsorbed, 100% of your glucose and amino acids, about half of your chloride, all right, and about 80 to 90% of bicarbonate is reabsorbed, all right? In terms of secretion, you have hydrogen ion secretion, ammonia, and urea, all right, are secreted in the PCT. I would be familiar with these percentages, okay? All right. Especially here, not so much in the other one.